So today's speaker is Dr. Matthew Pusey. Matthew did his PhD in physics at Imperial College in London in 2013. He graduated. He was supervised by Professor Terry Rudolph, and after his PhD, Dr. Pusey spent 3 years at the Parameter Institute for Theoretical Physics as a postdoctoral fellow, and then as a senior postdoctoral fellow. Then Matthew was awarded a research fellowship from the Royal Commission for the Exhibition of 1851. He held this fellowship at the Department of Computer Science at Wolfson College in Oxford. And in 2019, Dr. Pusey moved to York to take up an appointment as a lecturer in quantum information. And many of you will know the famous saying in natural science that if you think of a Python programming task and you have a question about it, then there will be at least 3 people who have answered it on Stack Exchange. There is a less well-known saying in quantum physics, which is that if you think of a foundational question in quantum mechanics, then there will be at least 3 papers from Matthew Pusey addressing it. So with these words, Matthew, the virtual floor is yours, and we're very, very thankful and happy to have you join us today.
Okay, thank you very much for that very nice introduction. I've just come from teaching. That was why I was a bit hurried showing up, and I have something at 12 o'clock straight afterwards as well. So I'm going to try and finish in fairly good time so that there's at least some time for discussion at the end. But just warning you that I will have to run. Okay, I'm going to try and share my screen. Okay, so what I wanted to tell you about today is a couple of papers involving various permutations of my collaborators, John Selby, David Schmid, Haoxing Du, and Rob Spekkens. And these are both about contextuality. The first one is about contextuality quite generally. It's just kind of a structure theorem that helps give us a bit of a better handle on how noncontextuality behaves, particularly in the context of transformations. So that's kind of a useful sort of framework type result. And then the second paper is actually applying that result to a particular case, which is the stabilizer subtheory in quantum mechanics. And it basically allows us to sort of have a classification that tells us exactly what non-contextual models there are of this theory. So that's just kind of illustrating the power of the structured theorem, hopefully. All right. So before I get into the details, since I said this is all about non-contextuality, I should introduce that for those who aren't totally familiar with it. So that's what I'm going to do in part 1. Contextuality is the failure of non-contextuality. And non-contextuality is a sort of fairly basic principle that you might hope your theory would satisfy, which is that your theory shouldn't have distinctions without a difference, or in Leibniz's terminology, you would want the identity of indiscernibles. So actually, we're going to apply this principle in a slightly more specific way. We're going to imagine that there's sort of 2 levels of description, that there's an operational level, which is the stuff we have direct access to, like the probabilities of different measurement outcomes. That's the stuff we're very familiar with using quantum theory to predict. So we have this operational level at the surface, but we're imagining that underneath there's an ontological level, which is the level of what's really going on objectively, whether anyone is there to measure it or not. Okay, so we're imagining that we have this operational level that we can have direct access to, and this ontological level that's kind of the underlying explanation for what we see at the operational level. And then this principle says that that we should expect that if two things are the same at the operational level, then the explanation for that is that they're the same at the ontological level. Or in other words,
I have a question here in the chat, Matthew. Sorry to interrupt you so early on. Someone asks, is the ontological identity a hidden variable?
Yeah, so what I'm calling this ontological level is broadly equivalent to what people sometimes call hidden variables. The only reason I don't use that terminology is that it's supposed to be a little bit more general. Like when people talk about hidden variables, they often think that we have the quantum state and then we have some extra hidden variables like you do in domain mechanics. So that would be one example of an ontology. But I want to be a bit more general, like I want to allow ontologies where the quantum state is not part of the ontology at all. So it's not the quantum state plus some hidden variables. It's just some different ontology where the quantum state isn't playing a role. And I also want to allow the possibility that the ontology is just the quantum state and nothing else, in which case there's kind of no hidden variables because there's nothing on top of the quantum state. But if you're used to thinking of hidden variables, it's pretty much fine to just substitute the word hidden variables in there.
So it's like, it's kind of what's physically real, right? Is that a good way? Yeah, okay. Thank you.
Okay. So we have this principle that there shouldn't be differences at the ontological level that aren't reflected at the operational level. So just to formalize that a bit, we set up this framework for how this ontology should look. So on the left-hand side of this equation, I have the operational level. So I'm imagining that I'm preparing my system somehow, I'm transforming it maybe, and then I'm measuring it, and I get some outcome K. And at the operational level, all I have are the probabilities for those different measurement outcomes, given the operations I've done to the system. And the kind of immediate thing you tend to notice about these things is that the probabilities of these measurement outcomes depends not just on what measurement you chose, but they depend on how you prepared and transformed the system. And the natural explanation for that is that when you prepared the system, there really was some physical system. It really did have some properties. When you transformed it, that had some effect on those properties. And when you measured it, that revealed some information about those properties. So this is just kind of the most naive explanation you could come up with of how you ended up with these probabilities. And that's exactly what we're going to do. So we're going to say when we prepare the system, there's this ontic state lambda. This is the real physical state of the system. And maybe the way you prepared it might not fix that physical state exactly. So there might be some probabilities for what that physical state is, depending on how you've prepared it. And then when we transform it, we're going to have a new ontic state that again might depend probabilistically on what the previous ontic state was and how you transformed it. And then when you measure it, the probabilities for the measurement outcomes are going to depend on this ontic state and which measurement you've done. And the kind of non-trivial assumption here is that this ontic state screens off the correlations between the preparations and the transformations and the measurement results. So in the ontological model, the outcome only depends on the preparation and the transformation via the ontic state lambda. There's no direct dependence on P and T here. Okay, but then we're equating this with what we see at the operational level, so we have to just marginalize over these ontic states because we're not going to see those at the operational level. Okay, so that's the basic framework of ontological models. There's one kind of technical point that I'm going to need at various points, which is sometimes the way you've prepared the system is that you just had some classical randomness, and with probability q, you prepared it one way, and with probability 1 minus q, you prepared it another way. Well, if these probabilities in the ontological model really are probabilities, then the overall probabilities for that procedure should just be the corresponding combination of the probabilities for the first procedure and the second procedure. Okay, so this is just exactly how you would expect to calculate this probability if you knew the probabilities for procedure 1 and procedure 2. Okay, so that's the ontological models framework. Now we're ready to impose this condition of noncontextuality. I should maybe just say, if you just have the basic framework, you can have an ontological model of any operational theory. The most trivial thing to do is just to make the ontic state to just be a description of the preparation. So in quantum theory, you could just make the ontic state the quantum state, and that would certainly satisfy this basic requirements for an ontological model. Okay, but to actually get something interesting, we're going to impose this, this principle of noncontextuality. And the principle was that there should be no distinctions at the ontological level that don't show up at the operational level. So the contrapositive of that is that if things are the same at the operational level, then they should be the same at the ontological level. So the way we formalize them being the same at the operational level, in the case of measurements, is we say that a measurement m and a measurement m primed are operationally equivalent if we get the same probabilities for that measurement on all preparations and transformations. Okay, so this first line is the notion that m and m primed are operationally equivalent. And then the principle of noncontextuality says that equivalence at the operational level should be reflected by an identity at the ontological level. And that's exactly what we're saying here. We're saying m and m primes have the same probabilities for all ontic states.
Sorry to disturb you, Matthew, and I think maybe the answer will be coming up. So here I have someone asking, does the same apply to different P's and different T's? I guess.
Yeah, so there's, just like this measurement noncontextuality, there's also preparation noncontextuality that says that if P is operationally equivalent to P primed, then the probability of lambda given P is equal to the probability of lambda given P primed. And there's a similar thing if T is operationally equivalent to T primed, they should be the same in the ontological model as well. And in fact, throughout this talk, I'm going to just assume all of that. So I'm just assuming what's this is sometimes called universal noncontextuality or Spekkens noncontextuality. Okay, so that's my principle of measurement noncontextuality. It's useful to have a slightly different way of talking about that, which is in quantum theory, for example, we know when a measurement m and a measurement m primed give the same statistics on all preparations and transformations. It's exactly when they're represented by the same PAVM. Okay, if two measurements are represented by the same PAVM, then they certainly give the same probabilities because the PAVM is the only thing you need to calculate the probabilities. And if they're represented by two different PAVMs, then there's at least one quantum state on which they give different probabilities. Okay, so m is equivalent to m primed if and only if they're represented by the same PAVM in quantum theory. So another way to encode this assumption in the case of quantum theory, for example, is just to say that the probabilities in your ontological model for some measurement outcome given your ontic state and the measurement are actually only a function of the PAVM. Okay, because if it's only a function of the PAVM, then whenever the measurements are equivalent, they're represented by the same PAVM, and since it's only depending on the PAVM, they would have to satisfy measurement noncontextuality. So that's just kind of another kind of a more compact and mathematically easier to work with way of expressing this assumption. It's just to say that the only information about the measurement you need to calculate the probabilities in the ontological model is the PAVM. Okay, I see there's a question about the post-measurement states. So in this talk, I'm always just kind of thinking
let's just read out the question for those
okay.
who listen to the recording. So the question is, even if two measurements have the same POVM, they might still have different state collapse effects. Should they still be regarded as distinct?
Yeah, so in this talk, I'm always kind of thinking of measurements destructively. I'm not caring about what the state is after the measurement. If you did care about that, then you would, the thing that you would check is whether they're represented by the same quantum instrument, basically. And if they were, then you would expect that the effect in the ontological model would be the same in that case. So that would look a bit more like transformation noncontextuality than measurement noncontextuality, because you would care not just about the probabilities of the measurement outcomes, but also about the new ontic state in that case. But yeah, in this talk, I'm only going to be thinking of these kind of destructive measurements where we're not talking about the system after the measurement. Okay. So that was my kind of quick introduction to the notion of contextuality that I'm going to be using. The other thing I need to introduce is some of the diagrams I'll be drawing. So these are basically just kind of quantum circuit diagrams, except for some reason, instead of time going from left to right, it goes from bottom to top. So this means I apply some transformation F in parallel with some transformation G. And after that, I apply H to the first system. Okay. I mean, I say these are quantum circuits. I'm not necessarily thinking of quantum theory here. I'm just thinking of any operational theory. A particular special case is a transformation that doesn't have any input. That's a preparation, which I draw like this, or a transformation that doesn't have any output. That's one of these destructive measurements, and I'll draw it like this. And I'll have a convention that if I kind of close the circuit by preparing all the systems at the start and measuring them all at the end, that I just take that overall thing to just be equal to the probability of getting that measurement outcome given that preparation and that transformation. Okay, so that's just a kind of convention for what these diagrams mean. And another convention I'll use is suppose two measurement outcomes are equivalent. So suppose that E and E primed give the same probabilities for all preparations. Remember I said when you close the circuit, that just gives you a probability. So that's what I was writing in equations before as being that these two measurements are equivalent. What I'm going to do in these diagrams is I'm going to say that this holds exactly when the diagram for that measurement, the first measurement, is equal to the diagram for the second measurement. So again, if we're talking about quantum theory here, that means that this E is just the POVM outcome. It doesn't have any other information about the measurement that isn't contained in the POVM. So this is just kind of useful because it basically means I'm baking in noncontextuality right into the way I draw the diagrams. It just kind of makes it a bit easier than imposing it separately. Okay, so far that's fairly standard. Something that's a bit less standard is we also have a diagrammatic notation for our ontological models. Okay, so everything here was at the operational level, but now we also have a diagrammatic notation for the ontological level. And what we do is we draw a blue box over something if we want to change it from being an operational thing to being an ontological thing. So if I draw a blue box over a preparation, then instead of talking about it at the operational level, I now talk about it at the ontological level, which means I'm talking about the probabilities of the ontic state coming out here, given this preparation. A thing we do that might be a bit hard to see is that we use thin lines for ontic states and we use thick lines for systems at the operational level. So when you put a box around something, you turn thick lines into thin lines. That shouldn't be too important. Likewise, I can put a blue box over a measurement, and that gives me the probabilities for that measurement outcome in the ontological model. And I can draw a blue box over a transformation, and that turns it into the probabilities for that transformation in the ontological model. Okay, and now I have a thin wire coming in at the bottom, that's the original ontic state lambda, and I have a thin wire coming out, that's the new ontic state lambda prime. Okay, and now I had this condition before for the ontological model to reproduce the operational probabilities. Well, now I can write that in diagrams. So on the left, I just have an operational thing. I said that when I close the circuit, that's just the probabilities. So the thing on the left is just these probabilities. And then we have a convention that when you connect the thin lines, then you're integrating over those ontic states. So that means the diagram on the right is just taking these three probabilities, that's the three blue boxes, and then because it's joined up, we just integrate over lambda and lambda prime. So this equation can be just written graphically in this way. Okay, so that's the notation that we're going to be using. Hopefully it will become a bit clearer why we're bothering with all these diagrams, because they do turn out to be quite useful. So now I'm ready to state the result from the first paper, which is the structure theorem that we proved. So the theorem uses two main assumptions. The first we call diagram preservation. So what this assumption says is that the diagrams at the operational level are kind of preserved when we get to the ontological level. So a particular case of that is that if we have this diagram on the left at the operational level, I put the blue box around it to go to the ontological level, I still have the same diagram, right? The blue boxes is just being split over those three things. And if I have that assumption, then the previous thing I talked about of the probabilities at the operational level being reproduced at the ontological level now just becomes this equation. Okay, so I would kind of call this an uncontroversial instance of diagram preservation, because this is kind of already built into everyone's version of the ontological models framework. Okay, it's kind of, whenever people set it up, they always assume that when you have a preparation, a transformation, and a measurement, you can split that up into the probabilities for the ontic state given the preparation, the effect of the transformation on the ontic states, and the probabilities for the measurements given the ontic state. Okay, so this was always built into the framework anyway, we're just expressing it diagrammatically. A slightly more controversial instance of diagram preservation, potentially, is that if I have the identity at the operational level, so this is like the identity channel in quantum theory, for example, then that should be represented by the identity at the ontological level. So in other words, if I do a transformation that has no effect at the operational level, then it has no effect on the ontic state. So the ontic state coming in here is the same as the ontic state coming out here. And that might sound a little bit dubious, because you could imagine some quite complicated way of implementing the identity transformation in quantum theory. You might do some complicated unitary and then do its inverse. Why should that have no effect at all on what's really going on? But another way you could do that, the identity transformation, is just to let 0 time elapse. And in that case, it's quite natural to think that nothing's going to happen to the ontic state. But then transformation noncontextuality says that anything that's operationally equivalent to letting 0 time elapse has to be represented in that same way in the ontological model. So given that we're assuming noncontextuality, I think it's a fairly defensible idea that identity at the operational level has to be identity at the ontological level. Okay, and another potentially controversial case is if I have a transformation that can be considered to be measuring the system, kind of throwing it away, but based on the result of the measurement preparing the system. So that's what's happening at the operational level. Diagram preservation would say that that's reflected at the ontological level. So at the ontological level, we really do just calculate the probabilities of that measurement outcome given the initial ontic state, and then totally forget about the initial ontic state and just produce a new ontic state in the usual way for that preparation. Okay, so the kind of lack of any side channel at the operational level is being reflected at the ontological level. There's no connection between the incoming ontic state and the outgoing ontic state, other than the fact that this preparation might depend on this measurement outcome. So in equations, I'm saying that the representation of the operational identity is just a kind of delta function on the ontic states. And I'm saying that the representation of this transformation factorizes into the representation of this preparation and the representation of this measurement. All right, so that's our first assumption, diagram preservation. Our second assumption is one that's fairly standard. It's something called local tomography, which says that basically you can determine what transformation you have just using product states and product measurements. So if two transformations are the same on all product states and product measurements, then they're just the same transformation. So this is satisfied by quantum theory. So this is why this is a fairly kind of standard assumption. Is also satisfied by classical probability theory. But it's not satisfied by every operational theory. For example, if you replaced the complex amplitudes in quantum theory with real numbers, then this wouldn't hold it. Okay, for our purposes, we need to just have a slightly different formulation of the assumption of local tomography, so we can prove that it's equivalent. And that's that a transformation can be written as a linear combination of these transformations where we measure and prepare the system. It's important that this is a linear combination, it's not a convex combination. So we're just saying that all transformations are kind of in the linear span of these measure and prepare transformations. It might be a little bit hard to get your head around why that's the case. Like why that's equivalent to local tomography as I defined it before. But in quantum theory, it's a fairly standard fact that the entangled states are in the linear span of the product states, right? Like the product states span the tensor product space. So any entangled state can be written as a linear combination of product states. It just can't be written as a convex combination of them. And if you put that fact through the Troy-Jamalkowski isomorphism, you exactly end up with this, because these kind of measure and prepare transformations are Troy-Jamalkowski isomorphic to product states. Okay, so that's our two assumptions. This diagram preservation about how the way things are fit together at the operational level, it has to be reflected at the ontological level. and this sort of fairly standard assumption of local tomography, which in particular is just true in quantum theory. So given those two assumptions, diagram preservation and local tomography, our structure theorem says that the representation of any transformation in such a model is given by just taking the transformation and composing it with a linear transformation chi and its inverse. Okay, so it's a little bit abstract at this point. It's helpful to just to kind of think about what is this chi that I've suddenly brought in. Okay, well, one special case of a transformation is a preparation. So in that case, we don't have a wire at the bottom. So that would just say that we put this chi afterwards. Okay, so in other words, the job that this chi plays is it just is a way of starting with the preparation at the operational level and turning it into the representation of that preparation at the ontological level. So this chi is just a gadget for going from the operational things to the probabilities of like lambda given p. Like, in other words, it's just a different way of doing this blue box over the preparation. So that means that what our structure theorem is saying is that once you've decided how the preparations are represented in your ontological model, like once you've decided what this chi thing is, you've automatically decided how the transformations are represented. They're represented by just using chi and its inverse. And you've automatically chosen how measurements are represented, because measurements are just a special case of transformation with no output. So they'll just be represented using chi inverse. So that's the kind of structure that the structure theorem finds. It's that the representations for the measurements, transformations, preparations, transformations, and measurements can't be chosen independently. Once you've chosen the representation of the preparations, you've fixed the entire ontological model. Okay. So I'm not doing too well on time, so I'll maybe just try and very quickly go through this proof, but don't worry if it doesn't make too much sense. Okay, so we use this version of the assumption of local tomography, where we turn the transformation into one of these linear combinations. We basically here just use convexity. You have to do a bit of work to turn that into linearity to allow us to pull these coefficients kind of out of the ontological model. And then we use diagram preservation to impose that the representation of these measure and prepare channels factorizes like this. The next step is just to consider the special case of preparations and basically just argue that there has to be some kind of linear map that represents how those preparations get turned into probabilities for the ontic states. And again, linearity here is just arrived at by starting with convexity and extending it a little bit. Okay, and likewise, the representation for measurements has to be some potentially different linear map phi. Okay, so combining those two things, we turn our representation of the transformations into this combination of the representation of measurements, preparations, and we've just kind of defined those representations using these gadgets chi and phi. And now we can just use the fact again that this combination is just a representation of the transformations and get back to here. And this is almost what we wanted, except we have these separate things here, chi and phi, whereas what we were aiming for was to have chi and chi inverse. So the final step is just to show that chi and phi are inverse to each other. And we do that by considering the operational representation, the ontological representation of the identity, which, just like as a special case of this thing, if I put the identity in here, then I just have phi followed by chi on the right-hand side. But by diagram preservation, that is just the identity at the ontological level, which means that this phi followed by this chi has to be the identity. And we also just consider a simple prepare and measure setup, look at that in the ontological model, split that into the probabilities for the preparation and the measurements, use the definition of this chi and phi, and then we use local tomography to say that basically this chi and phi never makes a difference to these preparation and measurement statistics. So at the local level, this looks like an identity, and then by local tomography, this really is the identity, basically. So we have that phi followed by chi as the identity, and we have that chi followed by phi as the identity. So they are each other's inverse, which is what we wanted. Okay, so that's our structure theorem. It says that there's kind of less freedom than you might expect when you're setting up an ontological model. You can only decide how to represent your preparations. Once you've done that, you've already fixed your representations of transformations and measurements. Okay, and so I'll now say a little bit about the second paper where we actually apply this to the particular case of the stabilizer subtheory of quantum theory. Okay, so if you've done any sort of quantum error correction or anything like that, you're probably fairly familiar with the subtheory. It's most often used in the case of qubits, but we care about it for qdits. So I'll just quickly run through the definition. So D is just the dimension of the Hilbert space we're working in. We use d roots of unity, and we have a kind of generalization of the Pauli X, that it just increments things in the computational basis modulo D, and a generalization of the Pauli Z, that it just gives us some power of omega. And if you take the product of some power of these X and Z, you get something that we call a Weyl operator, just indexed by P and Q. Weyl or Weyl, I never remember. Okay, so so these X and Zs are unitaries. The only other unitary we're going to care about is a sort of generalization of the Hadamard. So this is just kind of a d-dimensional version of the usual Hadamard gate. Formally, the subtheory we're talking about is the theory whose states are simultaneous eigenstates of a commuting set of these W observables. Measurements are just measurements of these observables, and transformations are generated by these unitaries, this Hadamard, and another phase gate that we don't need. Yeah, sorry, that was a little bit rushed, but if you've at least seen the qubit version of the stabilizer subtheory, then this is kind of a fairly natural generalization of that to qubits. Okay, so our result is that we're able to kind of completely classify what the non-contextual models are of this operational theory. And what we find is that in odd dimensions, there's exactly one non-contextual model. And in even dimensions, there are none. So in even dimensions, this theory is contextual. In odd dimensions, it's non-contextual, but there's only one non-contextual model of it. I don't think I'll try and explain the proof at all in the time I had, but the important thing is, relating to the first part of the talk, is that the first step is to apply our structure theorem to say that the ontological model has to have this structure. And in particular, one very useful thing we get from the structure theorem is that the number of ontic states in the ontological model has to be d squared, because we had that invertible map chi that went from the operational level to the ontological level. So for it to be invertible, the dimension of the input has to be equal to the dimension of the output. And the space of density operators has dimension d squared. So that invertibility means that the set of ontic states has to have size d squared in order to match that dimension. So that's very useful, because basically once we know how many ontic states there are, we can come up with a kind of smart labeling for them and then start doing various manipulations with them. And we basically sort of end up with some equations, and we find that in odd dimension, basically because 2 has an inverse mod d in odd dimension, there's a unique solution to those equations, and that gives us our unique ontological model. And in even dimensions, we find that the equations are inconsistent. So there's no non-contextual model. Okay, so what is that? What is that unique non-contextual model we find in d dimensions? In odd d, sorry. It's something called Gross's discrete Wigner function. It's something that's already been studied quite a lot. And so in a way, our result is kind of giving some kind of justification for the amount of attention that this particular way of representing the stabilizers subtheory has had. Because it's actually the unique non-contextual way of representing this theory. So the more normal way to think about this thing is as being a quasi-probability representation. That's normally how people talk about Wigner functions. But if a quasi-probability representation is non-negative, then you can also think of it as being an ontological model. So that's the ontological model we're talking about. And but kind of translating it back into that language of quasi-probabilities, what this result says is that if you have the entire stabilizer formalism, and then you have something that's represented negatively in Gross's discrete Wigner function, then there has to be contextuality, because Gross's discrete Wigner function was the only way to represent the stabilizer part positively. So if you chose a different representation, then some of the stabilizer part would be negative. But we've already said that this extra thing you had was negative in Gross's discrete Wigner function. So either way, you don't have an ontological model, a non-contextual model of the entire thing. And so this gives us a kind of another version of this result by Howard et al. That connected negativity in the discrete Wigner function to contextuality, with some kind of implications for magic state distillation and quantum computing. Okay, so to conclude, our structure theorem shows that at least in locally tomographic theories, non-contextual models have a surprisingly rigid structure. We can fix the number of ontic states, and once you've decided how to represent the preparations, you've fixed the representations of everything else. And in particular, if you see some model that doesn't satisfy the structure theorem, you can just sort of immediately say that it's contextual. So if you have an ontological model that has the wrong number of ontic states, like the number of ontic states is not equal to d squared in the case of quantum theory, then you immediately know that it's contextual. And if you're doing some kind of computation to search for non-contextual models, this makes your life a lot easier because now you know how many ontic states there are, and you know that you only need to vary the representation of the preparations. And then we applied that result to show that in odd dimensions, there's a unique non-contextual model of the stabilizer subtheory, which was Gross's discrete Wigner function. And in even dimensions, there's none at all, so there's contextuality in every even dimension. Okay, with that, I'll leave a little bit of time for questions.
Thanks a lot, Matthew, for a really interesting talk. I have one question myself, but I've got one question on the chat. So whilst other people prepare for potential questions, I'll read the question I've had in the chat, which is maybe not to do with contextuality so much, but asking why do you care about a Q-DITS stabilizer theory? Does anyone use that, or is it interesting from any other points of view?
So people have used it a little bit. Like there's, like, given how important the qubit stabilizer thing is for error correction, it's kind of a natural question that some people have investigated is whether it's useful at all to use higher dimensional stabilizer formalism. So, for example, some people have looked at whether magic state distillation might be more efficient using Q-trits or something like that. So there has been a little bit of interest on the kind of applied side. Foundationally, I think they're just quite interesting subtheories. Like the qubit one is already quite interesting because it has a lot of the stuff we find interesting about quantum theory. It has teleportation, it has an EPR paradox, it has like GHZ paradox and all kinds of stuff. And yet it's not universal for quantum computation. So it's this kind of microcosm that has some of the interesting stuff of quantum theory, but not all of it. And so that makes it quite an interesting playground foundationally. And the kind of interesting thing about looking at higher dimensions is basically precisely this thing of how it depends on whether the dimension is odd or even. So in odd dimensions, you get something that still looks kind of quantumish, and yet is classical in the sense of being non-contextual. Whereas in even dimensions, it does have contextuality, but it's still not universal for quantum computation. So yeah, it's just kind of an interesting collection of examples to think about foundationally, I think, with some kind of connections to the more applied side.
Okay, thanks. Crispin, you have a question.
Yes, so thanks for a very interesting talk. My question is really, have you thought about sort of testable things like Bell inequalities and something that might kind of one could do experimentally? And what I'm particularly interested in is, now that we have access to sort of many qubit quantum computers, are there things that we can test with those in principle?
Yeah, so it's I do kind of have another line of research which is looking at how to do experimental tests of contextuality, and I have collaborated with some experimentalists on doing that. I haven't yet kind of connected those two strands, so I haven't really looked at how this structure theorem stuff might be useful in doing those tests. But yeah, I think there's probably potential there for it to be useful. Kind of precisely because it kind of constrains things. It might sort of make it easier to do a test because there's kind of less things you need to rule out somehow.
Yeah.
But yeah, it's not something I've really thought about in detail yet.
No, it just struck me recently looking at the various tests that people have done, that they involve sort of 2 particles or 3 particles or something like that. But anyway, thanks very much. Thanks.
So I have another question for you, Matthew, which is more to do kind of as to do with non-contextuality and contextuality from a general perspective. So like every year there are a bunch of papers showing how you can show, you know, quantum contextuality in various settings. And I think last year Matthew Lostaglio, maybe 2 years ago, had this paper where he showed that if in most scenarios, if you can show that the measurement output of a quantum experiment has a non-zero quantum Fisher information, then you can conclude contextuality. So the question is, do you think that contextuality maybe is a quite kind of weak measure of quantumness, and that, you know, might be that loads and loads of things have contextuality, but it's not necessarily connected with supremacy or you know, quantum advantage from a technological point of view?
So I think the answer kind of depends on whether you're thinking about it qualitatively or quantitatively. So at the qualitative level, it is actually quite a strong notion of non-classicality, in that there's a lot of qualitative things that you might have thought were non-classical, like teleportation and no cloning and all these things that you can reproduce in non-contextual models. So at a qualitative level, it does give you quite a good sort of way of pinning down which are really the most interesting things about quantum theory. What's less clear is whether it tells you anything very useful at a quantitative level. So it's kind of often the case that, like, as soon as you put in a little bit of something truly quantum, you immediately have a failure of non-contextuality. And we don't really have a way of quantifying whether that's like a big enough failure to be interesting or useful or anything like that. So I think it does give you quite a good handle on which are the interesting features and which aren't, but it doesn't really yet give you a way of saying how interesting they are, I think.
Is there any kind of research projects to find kind of a von Neumann entropy of contextuality, saying how far your theory is from a non-contextual model or something like this? Or would that just be?
Yeah, some people have started to think about this, like sort of like setting up a resource theory of contextuality and finding monotones for it, that kind of thing. But yeah, I think there's still some work to do to kind of have a clear picture of that.
Okay. Well, thanks. I'm looking at my clock now. I think you have your hard deadline now, Matthew.
I do, yeah.
So thank you very much for joining us. I'll drop you an email later, maybe to reconnect about some things. But thank you so much for joining us.
Sure. Yeah, thanks a lot. That was fun.